Um, Welcome to the exciting location shoot that we're doing today. This is a hotel room in Boston, and that's going to make this far more exotic. So, in the first video, we saw how we could do the regression line using linear algebra, and you may not care because if you studied statistics, you already knew how to do this, or certainly if you didn't, there are statistical packages that let you do it that pretty easily. I will remind you that what we learned in 206 is actually an easier, faster way of finding a regression line, at least for a small number of data points. But, I mean, honestly, it tends to be faster even if you have 100 data points, even though the matrix is very large. But you have to write really, really tiny to do the computations. But one of the really nice things about what we did last time is that we saw how it works, right? It wasn't a magical formula that fell from the sky. And because of this, we're able to generalize pretty nicely, okay? So let's take the same points that we had before, okay? And instead of wanting to fit a line through those points, let's try to fit something more exotic, okay? So, for example, a quadratic, right? That's probably the next more exotic thing, I suppose. And so we can look at the theory that we developed last time and figure out how can it be adapted here. And really it's quite simple because, you know, we started with the model we were trying to find, right? And we used it to develop a set of equations. So let's return to that now. So this is how we're going to refer to our quadratic. It depends on three constants, beta 0, beta 1, and beta 2. And so, again, if the 4 points you're given lie on that quadratic, you'd have a system of linear equations. And those linear equations look like this. In general, it will be an inconsistent system, as you know, but we can use the theory of normal equations to find an approximate solution, and so a best-fitting quadratic. Here you see the computations involved. The matrix X is a little bit larger, and so you'd end up with a 3 by 3 when you do X transpose X, but it's really not much harder, especially if you have a computer in front of you, I suppose, to figure out these coefficients, and you get the best fitting quadratic, which is right here. So what you're seeing here is that quadratic sketched with the points that you saw before. Now if you think about it, the best fitting quadratic has to do as good a job as the best fitting line, if not better. You know, we can measure it using the distance from the projection, you know, the y minus y hat magnitude projection computation. And, you know, if the line actually did better than the parabola, well then when we did our system, we would have gotten beta 2 equal to 0, which is certainly possible. And so this is the general procedure, and that shouldn't be a shock. I think it doesn't take long to figure out how you make the adjustments from the linear version. So what I would like you to do now is to take the points that you considered before and to try to find the best fitting parabola through that. And you should pause at this point while you work it out because you don't want to give away the ending. There's a bit of a slow reveal because there's a lot of stuff to see here and you may want to pause. But you can check your work along the way. Notice that it's more calculations than you had before, but still rather doable. It's not a very pretty polynomial, but you know, I don't get paid to be pretty. And this again is your best fitting graph. Notice it does a better job than the line. So otherwise you'd have beta 2 equals to 0, as I said before. Okay, so that's not so bad, is it? And so next time on 206 the movie, we will look at even more extensions.